Alright, so today we're going to be talking about the Uniform Circular Motion Post Lab. Now, over the years, I've done various experiments and labs for this. Previously, I've done the rubber stopper with a tube tied through a string attached to a rubber stopper. This, unfortunately, doesn't yield great data. And most recently, we've been using the vernier devices, maybe even the Pasco devices in the future. And I've also done simulations from the physics classroom in order to do this lab. Regardless of which one we did, the post-lab discussion is pretty much the same. For the circular motion lab, what we did was we actually investigated 3 relationships. First, we did the net force versus the mass. Then we did the net force versus the radius. And then we did the net force versus velocity. We wanted to see how the net force was related to all 3 of these things, mass, radius, and velocity, for an object traveling in a circle with a constant speed. And it turns out that the mass versus net force relationship was linear. The net force versus the radius relationship was an inverse. So we had to straighten that one out by taking 1 over radius. That gave us a linear relationship. And the velocity graph was an upwards opening parabola. So what we had to do there was square velocity in order to get our straight line. Now, putting all these 3 things together, we were able to determine that the net force was linear with the mass. Net force was linear with the velocity squared, and net force was linear to 1 over the radius. Kind of mashing all 3 of those things together, we found that the net force, or from now on, we'll call it this centripetal force, is equal to the mass times the velocity squared over the radius. So all of these 3 things hold true, and they all hold true at once. So the centripetal force is directly proportional to mass, is directly proportional to the velocity squared, and it's directly proportional to 1 over the radius. So that gives us this equation for the centripetal force, or the net force for anything traveling in a circle at a constant speed. So over time, I've determined that there are 6 things that we can take away and say for anything that's undergoing uniform circular motion. The word uniform here just means that its speed is the same. So the first thing here is that the system or the object moves with a constant speed. The second thing is the system's velocity is not constant. Its direction changes. The third thing is the system's velocity is always tangent to the circle. The fourth thing is that the object is accelerating towards the center of the circle at all times. The fifth thing is the forces acting on the system are unbalanced. And the sixth thing is the net force points towards the center of the circle. Now, some of these things can be mushed up into one large one, but I prefer to just list them off like this. And I'll elaborate further on each one. Alright, so in this slide I'll talk about the first 3. The system moves with a constant speed. Now, anything that's traveling in a circle and it's undergoing uniform circular motion, its speed is constant. That means that every time it makes a circle, it does so in the same amount of time. So it travels through the same circumference over the same period of time. One example that we can take a look at is the Earth revolving around the sun. So every year it takes the same amount of time for the Earth to go around the sun. Now, the Earth technically doesn't make a perfect circle around the sun, but it's close enough. So here, every year is always the same length of time. And its path is always the same, so therefore its speed is constant. The second thing is the system's velocity is not constant. So for a second you may think, well, its speed is constant. How come its velocity is not constant? So the thing is that you have to remember that velocity is a vector. And velocity being a vector means that it has both a magnitude or a number, it has a value, and it also has a direction. Now, the thing about objects undergoing uniform circular motion is that its velocity changes. So, looking at our Earth here, yes, it's true. The Earth does have the same speed all throughout, but its velocity changes directions. So, when we take a look at the direction of the velocity, these arrows may be the same length. However, they always point different directions because the Earth's traveling in a circle. Likewise, if you take a ball and you spin it, attach it to a string and spin it over your head, that will also have the same velocity as long as you control it, but it will have different velocity, different directions at all times. So here it may go that way, and up here it may go that way. So it's possible for an object to have a constant speed, yet travel with a different direction at all times. The third thing here that I want to elaborate on is the object's velocity is always tangent to the circle. Now, what that means is that these velocities will always just hit the circle at one point. So you can recall the demo that I did in class where I tied a buggy car to a ring stand and I allowed it to travel in a circle. When I cut the buggy car free of the string, it traveled in a path that was tangent to the circle that I was traveling in. Alright, so these next couple of slides, I'm going to talk about 4, 5, and 6. So the object is changing in terms of its velocity. So if its velocity is changing, that means it has to be accelerating. Now, in which direction is it accelerating? Here we're going to take a look at the Earth and Sun system again. Now we have the velocity of the Earth. It's tangent to the circle that it travels in. And the only thing, if we were to draw a force diagram about the Earth, the only thing that we would see for the force diagram is this force of gravity on the Earth by the sun. And at all times, that force points towards the sun. It's also the net force. So that's about problem number 6, where we're talking about the net force, or the centripetal force, always points towards the center of the circle. Now, it just so happens that that net force, or that centripetal force, can be made up of any force depending on the situation. For example, here we have force of gravity because the Earth is attracted to the sun via gravity. Now, in the previous slide, we talked about someone whirling a ball attached to a string above their head. In that case, we can't say that was the force of gravity that's causing the circular motion. It's the force of tension in that string. Now, for the acceleration, since the net force in this problem is the force of gravity, the acceleration also points in the same direction. So that's why the acceleration points towards the center of the circle. So here I kind of just want to elaborate more on the net force, aka the centripetal force that we've been talking about. I'm going to talk about the Ferris wheel problem. So here I have 4 dinosaurs riding a Ferris wheel, and I'm going to start off by doing a force diagram for this top one. So at the top, the dinosaur, I'm going to draw part of its path here. The dinosaur has 2 forces acting on it. It's got a normal force and the force of gravity. Now, remember, in the previous slide, we said that the centripetal force has to point in the same direction as it has to point towards the center of the circle. Now, if the dinosaur were sitting on flat ground and not moving at all, we could say that there's a normal force on the dino by the floor, and then there's also the force of gravity on the dino by the earth. And that we can also say that these are equal vectors. Now, in order for this to have a net force, we have to think about the forces acting on how long they should be. We want to make sure that the force that points towards the center is always the longest. Now, in this case, for the top dinosaur, we've got a force of gravity that points downwards. And it's also got a normal force because it's sitting on that platform. So we have to be careful with how we draw this. Because it's accelerating, we have to make sure that the forces are unbalanced. And in order for it to have circular motion, the one that points towards the center has to be longer. So I'm going to purposefully draw the normal force shorter than the force of gravity. And that's what we want. We want to make sure that that net force is always pointing towards the center. So again, I don't draw the net force on force diagrams, but you want to make sure that the net force points towards the center there. Now we can also do the same thing for the dinosaur at the bottom. And we'll find, and I'll draw the trajectory here. We'll find a similar but slightly different situation. Now here, this force of gravity for the dinosaur at the bottom, sorry, I want to identify my system. The dinosaur at the bottom here that's yawning, we've got the same force of gravity, assuming that these dinosaurs all have the same mass. Same force of gravity as its friend up top. So again, we want to make sure that the force that points towards the center is the longest force. In order to do that, the normal force has to be the longer one. So you want to make sure that if this were a quiz or test, you draw this visually longer so that I can tell that you mean to draw the normal force longer. So for the dinosaur at the bottom, the net force that one experiences points upwards, like that. So we've got the net force here. But at all times, that net force has to point towards the center of the circle. All right, so just a few ideas to get you started, get you thinking about our homework problems. But we'll talk more about this in class.